Okay, so now we're ready to finish section 3.1. Um, one thing that's in that section that's kind of important and kind of trivial is the equality between two vectors. So when are two vectors equal between two vectors? Geometrically, it occurs when two vectors have the same length and direction. So this vector and this vector are equal. Okay. Algebraically, what does it mean if I have a vector v? Let's say that's equal to a vector u, and we're in two space. That means that if I write them with their coordinates, u1 v2 v1 v2 is the same as u2. I'm gonna get it right. v1 v2 is the same as u1 u2, and the two vectors are going to be equal. Okay, when each component matches the one you find on the other side. So v1 has to be the same as u1, and v2 has to be the same as u2. Okay, so this is the kind of thing you're going to want to show if you want to show algebraically that two vectors are equal. So that brings us to a theorem in the book. So I wanted you to look at it. It's theorem 3.1.1. So pause the video, look at it. It lists important properties of vector operations. Now, if you look at part A, it says that u plus v is the same as v plus u. That's commutativity. Okay, so I want to write. So A is the commutativity property of commutativity of vector addition. That's what it is. Part B, you'll recognize what we have looked at in the previous video. It's the associativity of vector addition. Okay. C is the it says that u plus 0, the 0 vector, is 0 plus u. Note how 0 is in bold. It means that 0 is considered as a vector here. So that's basically the property of the 0 vector. U plus negative u is 0, so that's the property of the negative of the opposite of u, or the negative of u. So the one I want to look at right now is E. E says, and I'm going to write this one up. It says k times u plus v. Now notice how k is not bold here. That means that and u and v are bold. So that means u and v are vectors and k is a scalar. So this is a multiplication of a scalar by an addition of two vectors, and basically the k will distribute over the addition. Okay. Now, how do we prove something like this? Well, we exactly have something where a statement where two vectors are said to be equal. So this vector here is equal to this vector there. So how do we prove that? Well, we're going to show that on each side the components of the first vector matches the components of the vector that's on the right hand side of the equality sign. Okay, so how do we do this? Let's look at this. So I will start. Usually, to prove a statement like this, you start with one side and you try to get to the other side. So usually you pick the side that's the most complicated and you try to get to the side that's the least complicated. But that doesn't mean it's not a rule. But usually I find that helps. In this case, both sides are just as complicated or as easy, so as simple. So I'm going to choose one and try to get to the other. So here's my goal, right? I started with one side. I'm just going to start with the left hand side. So I'm going to do a whole bunch of, well, I'm going to rewrite this until I eventually get to the other side. So that's my goal. Okay, so let's keep that in mind. Now, k times u plus v, I will write that in terms of first their components. So u u is u1 u2 plus v1 v2. Okay, and k is a scalar, so it's just a real number. Right now, everything's a real number here. That's a real number, that's a real number, that's a real number, that's a real number, and that's a real number. Okay, they're all scalars and so on. Okay, so any property of real numbers can be applied to those variables here. Okay, now what I have here inside the bracket is an addition between two vectors, so I know that by the definition of vector addition, I can match their components and add them up. So u1 plus v1, u2 plus v2, like this. This is, and on this side, I can, on the right hand side, I can add what just happened. So I've applied the property of vector addition. Here we go. Now, what's next? Now I want to multiply the scalar k by the vector here. So what's interesting now is I have a single vector now. Okay, and you'll recall that if I have, let's say, a scalar that's multiplied by a vector, the scalar, it scales the vector, so it makes it it will make it 7 times as long here in my little example here. So all we need to do is multiply 7 by each of the components of the vector. So this is what I'm going to do now in my proof. I'm going to multiply k by the components of the vector, like this. Okay, so this is scalar multiplication I have used here. So I'm going to need more steps. I'm going to erase this, but eventually this is where I want to get to. Okay, now inside here I've told you, right, everything's a real number, the k, the u1, the v1, okay, and the other ones too. So now I can apply properties of real numbers to these guys. So for example, this thing here, that's a multiplication of a real number by a sum of real numbers. So I can distribute the k over the addition of the real numbers. So that's going to be ku1 plus kv1, and over here it's ku2 plus kv2. Okay, and finally I will split this up. You see this here, I have two numbers each time that are added up, so I can split this vector into the sum of two vectors, like this. So this is reapplying vector addition. So this is vector addition again, but the other way around. And I can pull out the k now. So I'm going backwards with scalar multiplication. So this is scalar multiplication again. And this is exactly ku plus kv, and I'm done. And in a proof, usually when we're done, we write a little square like this. This means this guy here, it means end of proof. So see that in this course, one of the goal of the course is to teach you how to do proofs, and how to prove things are to argue. So often the proofs will involve an equality you need to show. So you're going to need to start with one side and try to get to the other side like I just did. Okay, notice how everything's lined up, right? So I've got the left hand side, I've got the right hand side, and in between I've got equivalent expressions. It's not necessary to repeat this part. You don't need to repeat this part. It's kind of assumed that well, you start with this, and this is equal to the next thing, which is equal to the next thing, so eventually everything's equal here. What I don't want you to do is play with both sides at the same time. Okay, it creates confusion. So I don't want you to start playing around with this side at the same time as you play around with the right hand side. Okay, so stick to one side, to, well, one expression, and then write on the right hand side equivalent expressions until you get the other expression that you want to show the first one is equal to. All right.